Hi there. This time we're going to talk about modularity. And one of the reasons to talk about modularity is hands-on possibilities that you get if you have a modular system that you can start constructing with. And this actually has an impact on the way that we may learn, the way that we may interact with our systems. If we go back in time, Piaget defined what he calls constructionism based on constructivism, where he's saying that the best way of learning is through creating the system that you're about to learn about. So the best way is that you can, by yourself, try to create that system. And when you're creating that system, you're learning about that system and the principles that may govern this system, the mathematical rules, the engineering principles, and whatever this may be. So the important thing is that you have a hands-on problem-solving constructionism. And in this way, you can say that you can confront some abstract cognitive problem solving in a simpler manner through the physical representation that it may have. And by the modularity, we are striving to create systems that allow you to, in an easy manner, to do this kind of physical manipulation. With the modules, we give a physical representation of the more abstract things so that you can easily construct this. And this, of course, has an influence for us when we're talking about Playware, and specifically the Playware ABC. Remember, we're trying to make technology for anybody, anywhere, anytime by B, building bodies and brains, that C, facilitates that people can construct, combine, and create. Here you see the construct, combine, and create. That's really where we get into this kind of constructionism. And the B, building bodies and brains, you'll see in this lecture here, we are allowing, with the modularity, we allow you to physically start building bodies and brains. And again, that hopefully we can make those systems so easily available that it can be used by anybody, anywhere, anytime. Now, you remember we talked earlier about about building bodies and brains, that in the past, if we go back in time, the first, let's say, 50 years of robotics was fairly much based on the old approach that you would either buy an expensive robot or you would use years to engineer a robot. Then on the other, and you would use your research time on making the AI software, the artificial intelligence, the brain of the robot, and then you would download that software to the robot, to the body, and then you would test that body. And then later on in the late 90s came out things like the Lego Mindstorms robots that suddenly allowed people to start building very easily, very fast, the bodies of the robots. So people were able to build the robots, and then by afterwards understanding the syntax and semantics of a programming language, even a graphical one, they could start programming this, download their program, the brain to the robot, start testing and debugging that, and then finally play with the robots. Now, what we're saying here today, when we're talking about modularity and what I would term modular building blocks, is we can put all that into one process where we have action in the interaction. As soon as people start building with modules, they are playing, they are interacting, and they get an immediate feedback from that kind of building. So there's not any more the long process from the building to the play or the interaction. It's all in one. Now, to understand this this better, you can think about in the previous videos we have been touching upon behavior-based systems, where in software we developed agents for computer games or for some physical objects, for robots and for Playware. But in those cases, this was thought of as the software, the brain. So the behavior-based system that we also see sketched here on the top, these were several behaviors running in parallel that all had access to the senses, and they could access the actuators. And we talked about how to coordinate between these many behaviors that would like to control the actuators. Now, as we said, these were software modules, these behaviors there. But we can also imagine, if we go down here and say, well, imagine these are physical building blocks. Each behavior is a physical building block. And when you put these physical building blocks together, you're not only creating the physical structure, but you're also creating this coordination of the actuators, this putting together of the behaviors in a certain manner will signify a coordination of the actuators over here. So you are at one time building bodies and brains. Now, this is in contrast with the good old-fashioned way of creating intelligent robots. In the past, there would be a split between the body on one side and the brain on the other side, between the hardware on one side and the software on the other side, between the building on one side and the programming on the other side. So if we look at the image here, we would say that in the good old days, to create an intelligent robot, we would on one side have to make some hardware through engineering, a body shell, and then on the other side, we would have to make some software, which was based on some artificial intelligence research. We would do a lot of work, especially on this side of doing the AI research, try to make the brain as intelligent, as good as possible. And when we would finally have used, say, years to develop a good brain, researchers would then think we could just put that into the body, into the shell, and then that would control the robots. Now, that kind of idea became challenged a couple of decades ago, when researchers started to say that, well, this is not so simple, because there's an interplay, there's an intimate interplay between the body and the brain, also between the body and the surrounding environment, between the robot and the dynamics of whatever happens around the robot. So maybe this cannot be solved like this, that there's an influence of the environment and the material. We saw that last time we talked about the humanoid robots, how the body flexibility, the springs, the material properties, the environment, when the other players in the environment would have touched the ball, how could you then control if you are using the good old-fashioned way? Instead, we needed something where there was an interplay between all these different parameters playing a role, and not only saying that the only thing important here is the software, is the AI in the software, but it's actually all those parameters together that we need to look at. So there is a big role of the body. And again, to explore that, we can explore that by splitting the body into, we could say, robotic building blocks, like we see here. So where we say that a robotic building block is defined as having a physical expression, it's able to process, and then it's able to communicate with its surrounding environment. And that communication can, for instance, be to neighboring building blocks or through sensing or actuation. So in this case, if we have many building blocks, we would say the robot is constituted by the assemblage of all those building blocks. So we would say that the overall behavior of a robotic artifact emerges from the coordination of a number of building blocks that each represent a primitive behavior. As we had in the behavior-based system, each building block is like a behavior, and we put those together, and then together, as we see on the video, that constitutes the robot, and together a certain behavior emerges from this. And you remember we talked about emergence earlier. Here in the video, we made a simulation of 7,000 modules following some chemical trails, and that would then lead to giving a certain body structure, as you can see here, when they're crawling upon each other. Something else emerges than just 7,000 modules, namely a certain structure. So you remember the emergence, we talked about that emergent behavior. We would say is the complex behavior that can arise from simple rules where the sum of the rules is more than just the single rules put together, but there's a complex behavior that arises from that correct interplay. For instance, when we see flock of birds flying around, or a school of fish, or we talked about the example on the stadium with fans doing the Mexican wave, for instance. So the behavior emerges from many simple agents that each have their simple behavior, but when they're put together, all these simple agents with the behavior, something bigger emerges. And that's what we're trying to do when we're creating the building blocks. So the building blocks are the small simple agents with simple rules, and then we put many of these building blocks together, physical building blocks, and something larger something coordinated emerges from that. So one example of that is something like this. We created this in the HYDRA project, this self-reconfigurable robots that can shape shift, that can change its own shape. As you may have seen, for instance, in films like Terminator, where you have one that can melt into another shape. So this we can actually do with physical robots. If we think about the robot being built up of many atoms or many cells that are small robotic building blocks that can attach to each other, as we see here. They can move on each other, and they can change the shape from being a snake to a chair to a car, or whatever we may think of. Or as in the little cartoon here on the bottom, imagine a robot driving over to some place, then it crawls up on the ground here, and then it makes itself into a snake and into maybe a column here under after an earthquake. If this is a building that has collapsed, then you can imagine this kind of rescue robot driving over there, crawling up, make itself into a snake, into a small hole, into the fundament, into the base of the building, and where it has collapsed, make itself into one or more columns that can sustain this until rescue workers can move in. And in this case, you see, we exploit this fact about being able to shift. So we explored that in this project here, trying to create this building blocks for self-designing artifacts. And the inspiration came from the HYDRA, from developmental biology, where you see on the video, this is a HYDRA. You can actually cut this small amoeba, and then after a short while, it will change itself into the original shape again. It will grow its own shape, so to speak. So we took the inspiration from that and say, can we, in a similar manner, from the engineering point of view, create these artifacts that can grow their own shape, that can shift their shape from one shape to another. So in order to do so, we need to define the hardware building blocks, where again we say that each building block includes processing and communication, and they can attach to each other. And then, of course, we need to optimize the control and the physical shape. So we can take some inspiration from biology when we do this, from morphogenesis, as was done here by our colleagues from Zurich, where they're creating arbitrary shapes from these spring qualities. If the modules, you can see many modules here, and then if they have the attachment have different spring qualities, then it will define different shapes to emerge. The shapes will emerge when these springs have the different constants, as you can see on these images here in simulation. So we can start doing simulation of this. We can also start to simulate more precisely some modules that we would like to develop, like here, the ATRON modules. And for doing that, we looked at many different kind of shapes and attachment structures and so forth. And we came up with this inspiration from certain atomic structures, where we said that the sphere, this would be, we would develop the modules as spheres that could rotate around equator and have 8 connection points. So points where they could connect to each other, and then they would be arranged in a, as we can see here on the bottom right, in a surface-centered qubit lattice, so that they would be able to connect in these different points, as we can also see on the photo here of a very early, the first prototype of this system. And then we could start having defined that, we could start making a simulator and look at, can we do self-reconfiguration without actually building this in physics to begin with, but look at how can these modules attach to each other, traverse over the structure to make new kind of shapes, or to make actual movements. As you see here, this is a movement translating itself from one position to the next position, one step ahead. You can see in a while it will have made a full transition. Here it has made one step. Now it's going to take a second step where it translates itself from the previous position to the next position, and you'll see in a while now it has taken one more step. So you can see it can by this crawl over the surface. So having that in simulation, we started to look at how can we create this in a physical form. As I said, with spheres that rotate around the equator, they have 8 attachment points. What you can see in the drawing here, that here is one attachment point. This is a male gripper. So there's some male grippers like this coming from the top and then also from the bottom. And they can go around like this, as I show with my fingers here, like this, to grasp around a bar, which is the female connector. They do like this and grasp around the bar. The bar you can see is here on this side here, is this bar here. Or if we take it up on this image to the right, you can see the bar here where it attaches. And then say in the middle, it can rotate around equator attached to neighboring modules. What we also did was that we actually put on the connectors an attachment point so that they could share the energy, the battery energy from there. And just to say the way that we developed this, and you may remember from the second video in this series, that we were talking about if we want to go to bring our research from prototypes out to the real world, and even in the end out to the real market, one of the best ways that we see doing that is through an iterative model, a cyclic model, where we're doing fast prototyping in this iterative fashion. So we get an idea, we make a design, we implement that design in a very fast manner as a fast prototype. Then we try this one out, we test it and evaluate how it goes. And based on that, we make requirements to the next prototype round. So we again are having analyzed the first ones in experiments. We build a new prototype. We test this, deploy and test this again. We evaluate how this goes. We by that evaluation, we come up with new requirements and we make the next prototype. So actually using this cyclic model, we can refine this step by step. So one of the first prototype rounds looked like this, where you can see the attachment mechanism is quite different. Here you had we were making some screws that would go out and they would go into this female connector here. And that worked to some degree, but not really to our satisfaction. Another one, prototype round, you see on the upper left corner here, the image here, with 3D printed shell here, with the connectors, as I talked about before, with the screws going out. Figuring out that didn't work, so we made another kind of female. You can see the female connector here, the hole here, and then some grippers going out like this. And then later on came prototype round 3 here, and round 4 here, which is more the ones that I talked about before, with this male and female grippers, as I talked about before, and the energy sharing and so forth, and a better mechanism for turning around equator with this. So then you can see in the end, finally, with the shell around it, with the light blue shell around it, modules like this, as you saw previously on the video. So again, an iterative development in cycles based on fast prototyping. In this case here, to create the self-reconfigurable robots, the shape-shifting robots that by themselves could optimize on their physical shape. But even as you see on the image here, it could be interesting to explore what does this mean also in terms of user interaction, because now what we have talked about here is self-reconfigurable robots, making the robots do everything by themselves. So is this always the case, that this is best to strive for fully autonomous robots? Or could we imagine actually that what we're seeing is that fully autonomous robots may be good for some things, but in other cases we need the human interaction, so that we may be able to go from self-reconfiguration to user reconfiguration. And that's quite interesting, because often when we think about intelligence and intelligent machines, intelligent robots, we think of how can we create all this intelligence inside the robot, as part of the robot, and even as we talked about in the interplay between the body and the brain, and the structure, the material, but everything controlled in the robot, self-steered, self-developed by the robot. Now, we may actually think that this may not be the optimal way of creating an intelligent response to a challenge that you may have. Because in many cases, may be that the intelligence is actually what arises from an interplay between, on one side, the intelligent, or let's say half intelligent artifact, and yourself, you as a human being, in your interaction with that partly intelligent robot, partly intelligent artifact, with that machine. So the intelligence is what you are creating together between your intelligence that you have and the one that's in the artificial one that's created in the machine, in the artifact. So you could think of, instead of striving for creating fully autonomous robots, you could maybe much better create robots that are user configurable, where the intelligence comes from the interplay between you as the human being, the human user, and the artifact. So it's the interplay that creates the intelligent response. So just I made this small kind of comic drawing here. Imagine this case. On the left side, we have a small kitchen robot that's supposed to do things in the kitchen. Now, if this for its task is supposed to reach up for getting something up on this shelf up here, well, that's difficult because it's a small robot. It cannot reach there. So you need to do a lot of control for it to be able to jump up on the table and reach up with its hand to grasp this thing. So maybe it's actually in that case much easier if you have a user configurable modular robot where you can click, click, click. You can extend the arm, make the arm long enough, and put on a hand so that it can reach up. So it can go up and reach up there on the shelf, pick the item that it needs and take it down. So you click, click, click very easily helps the robot to become a different physical shape with different gripper on and so forth. And then by that, it's able to solve the task. By that, you may have been using partly your intelligence, partly that of the system that has been created. So together, you are creating the intelligent response. Now imagine this thought, or you think about, can you actually do this? Can you actually make systems where this is possible? Well, in this case here, you can look at the girl here. She's actually able to take modules that are created here and say, click, 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 click. I put this module simply together. I create some kind of torso robot, and then I interact with this torso. I wave the arms and the torso waves the arms. I put my arms above my head. The torso mimics what I'm doing, put the arms above the head and so forth. So she is on the left side, she's quickly building the robot, and then she starts interacting with the robot. And here again, what we have done is we have split the robot into robotic building blocks, and we allow the user to build with this robot. So by physically building, she is creating both the body and the brain of the robot. So let's look at this in a couple of small videos. Yeah, this is the Fable modular robot that we created in a larger project, and especially this was headed by Moises and David really worked a lot of this in our larger project on creating user interactive modular robots. You can see on one side, click, 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 make a spider. On the right side, click, click, make this kind of moving arms. So they have taken this further to create the Fable system to make it easy for anyone to build and program robots. Again, split this up to modules, many modules for sensors, modules for construction, modules for actuation. And then with this, you can build many different things. You have one system, but many learning opportunities. You can learn programming, math, physics while building the robots. If you, for instance, use this in an educational setting, with things, programming languages like some graphical programming languages like Blockly, or you can open up the box of the programming modules and see what's inside with things like Python. So they can do scaffolding like this. And here you can see a short video of the Fable robot system. Click, 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 build a robot, and then you can start steering the robot. You can have other navigation modules like this. If you're more interested in this, go look at shaperobotics.com. It's really fantastic work. Now, another example of this building bodies and brains, which we have touched upon before, is this example with these physical interactive tiles that have now become the motor tiles that you can take anywhere and put them together to make different physical configurations. And by the interaction, you are creating the intelligent response. People take this within 1 minute, set them up. The structure by itself detects what is the physical layout and then adjust the level and the activities to match the physical shape of the body. So you can say that the modules, when put together, they constitute the body, and then the software constitutes the brain. And that allows for an easy interaction with the user after having created this physical reconfiguration of the system. And this is easily done, just splitting this apart and put this together as a puzzle. And you can build different shapes, you can build them in different size depending on what you may need, as we see here. On the left side, you have a child who can reach a certain part, so the physiotherapist built a certain shape for her. Or on the right side, the child with minor cerebral palsy, she can do a little bit further, so they built another shape. So the therapist here is simply changing the activity by the physical construction. She's building the body, so to speak, the physical shape, the body. And you see actually the software is the same, but what has been changed is the body shape, the physical layout, and that changes the activity in a very easy manner. So it's important, this thing, that when you want to optimize, you can optimize both on the body and on the brain, which is often forgotten when we are talking about creating intelligent systems. They tend to forget the importance of the body, of the physical building, but only think about that they can optimize by optimizing the software. So now, but building with the blocks is actually important. Here we can also see, by splitting things up to blocks, we can use this, in this case, with the hospitalized children, where we say that we make different representations of difficult things with the physical modules. So in this case, we say that there's a representational determinism, that different isomorphic representation of a formal structure can cause grammatical different cognitive behavior. And I will give you the example of this thing with the importance of the physical shape here, with things like the building blocks. It could be, as we saw before, it could be this cubic shapes that we have here, where they're touching the sensors, or it could be things like Lego blocks here. Now, if I go back here with this forms here, what we do is we say that when we make things into physical shapes and physical manipulation, we are making some things more easy to understand. We're making some cognitive challenges easier to understand. And we do that simply by taking these difficult things like difficult mathematics or difficult engineering, or what you may find quite difficult. Imagine you can change that into something physical that you can manipulate. Then maybe it's more easy for you to tackle, more easy for you to understand. I will give just the most simple example you can think about is when you have small children, maybe the age of those that you see in the images here. If you want to learn them how to add numbers, it may be difficult for them to understand what do you mean when you say addition, and what do you mean when you say 3 plus 2. Well, that's very abstract thinking, and it's not so easy. Now, if you say, okay, let's try to change the representation to a physical representation. Try to use your fingers. Remember, we're saying 3 plus 2. So we say, use your fingers. You say 1, 2, 3 plus 2, 1, 2. What does that give you? That gives you 1, 2, 3, 4, 5. 5. So that's easy to understand because we have changed the representation from very abstract, invisible thinking to something concrete, something visible. We've used our fingers, or we could use 3 plus 2 apples you lay on the table, and you look, okay, how many do you have? So in this case, we have this, as I say, this different isomorphic representation that when we change that from the abstract representation to the physical representation, that dramatically changed the cognitive load for you for understanding how to solve this problem. So of course we can think of that in terms of, this is essentially like Lego blocks. So what we're thinking about is, with the Lego blocks, couldn't we imagine this? Imagine the Lego blocks would have you're not only building a physical structure, but if we put a small computer inside each Lego blocks, then we have this kind of robotic building blocks. So we can do programming by building. So we are not only creating the physical form, but also the behavior of that form. The long-term dream, which we're not doing now, but you could imagine this vision. If you build a horse, the behavior should also be a horse behavior of this thing that you're building, the horse that you're building. So imagine this. This is like Lego blocks with processing power inside each Lego block. And we can actually do that. So one very early prototype of this, we would just put a small processor inside each Lego block, and then the connectors of the Lego blocks, you can see here underneath, this part here, this part here, they would also be two-way communication connectors between the blocks, between that block and the block that they connect to. And there would be energy transfer also in the corners here and in the studs on top of the Lego blocks. And then we would create a number of different different kind of intelligent Lego blocks. There will be some standard blocks that would be doing processing and communication, and the battery block as well. And then there would be some input blocks and output blocks. And the input blocks could be light sensors, could be microphones, infrared light sensors, touch sensors, potentiometers for turning around. Output building blocks could be things like a motor block of different kinds that could turn, or all the way with an axe inside. Could be light diodes, it could be sound generators, IR emitters for infrared wireless communication, could be a display block, and so forth. So imagine you could have a number of different intelligent Lego blocks. And then you can imagine that we have this standard building block, input building blocks, and output building blocks. You put this together, and as soon as you put this together, you can interact with them. Here's a battery, a microphone, and a motor. And you can see as soon as one claps, it reacts. Very simple here. But of course, then we need to understand how should the processing be inside these intelligent Lego blocks in order for the overall behavior to emerge in the right manner. So you can imagine the processing inside such a robotic building block, such an intelligent Lego block, to be of many different kinds. It could, for instance, be an arithmetic brick, where each individual brick is performing some arithmetic operation like addition, subtraction, multiplication, division, and so forth. You could also imagine this being each block being a neural block, in this sense that each block is a neuron in an artificial neuron. And then if by putting more blocks together, the communication channels are the connections, or the synapses, as we call them, in an artificial neural network. So when you put the blocks together, they physically create a physical artificial neural network. The same goes for cellular automata. You could imagine that, where the knowledge is based on what is activated in the neighbors. Or you could think of, as we had in the previous videos when we were talking about behavior-based systems, inspired by Rodney Brooks's behavior-based systems and the subsumption architecture. You could think of this, that each brick has a primitive behavior, and when you put more bricks together, the combination is what gives you the arbitration in terms of making a sequence, or switching between these, or fusion between these different behaviors. So just to take the example here of the modules being arithmetic bricks. Imagine here that we want to create something like the expression that we have here, parenthesis x plus y, parenthesis n times z. We would like to make that in the blocks with these blocks here. By doing that, we can explore how different physical buildings, different morphologies, as we call it, will result in different functionalities of the structure built by the user. And let's look at it here. In this case, the user puts on a module. You can see on the display that module had the value of 24. The next module, you can see now in the display, say value 6. It has the value of 6. Now he puts on the blue module. There is a multiplication. So it multiplies. Here you have, sorry, this was addition. So he adds this 24 plus 6 was 30. Has another value, module 2. and puts on, now comes the multiplication, times 2 times the one he had before, 24 plus 6, 30, times 2 gives you 60, right? And that's all fine, and as it should be. But now imagine that we change the physical layout, we change the morphology slightly here, that instead of having the multiplication block here, as I point to with the pointer here, the lower blue one, if we raise that one level and put the blue block up here, where I have the pointer now, so then we will have the blue block here and the red block up here, then the only thing we have done is we have raised this lower one up one level. We have changed the morphology slightly. But what would happen there by doing that is in fact that we are moving the parenthesis over from being around the x plus y to being around the parenthesis to be around y times c. So that means that we would get, as we have here on the lower left here, down here, we have the expressions that we calculate, that initially we had 24 plus 6 times 2 equals 60. Now we would have, if we move that up one level, we would have that we first calculate 6 times 2, giving us 12, plus 24, the total will give us 36. So of course, this is a very simple, and you would probably think stupid example. Yes, that's true, but it has a very, very important point, namely that different physical shapes gives you different functionalities. Different morphologies gives you different functionalities, or in other words, different body shapes results in different behavior. So the body influences the overall response, the overall functionality of this entity, of this artificial being, or whatever we want to call this artifact. And that's an important point to remember, that the body has an important influence of the resulting behavior of the intelligent artifact, of the intelligent agent, of the even us, the human being. The different shapes have different consequences for different natural being, for different animals, for instance. So you cannot only think about optimizing the software, the intelligent brain, so to speak, without thinking about which body is this going to control afterwards. That's a flaw in terms of the science, if you think that you can just abstract the body away and then only think about intelligent software, so to speak, the brain. There is an intimate relationship between the body and the brain, and that is why in the Playware ABC we're also talking about the B, building bodies and brains. Now, the building blocks can, of course, be more sophisticated also in terms of their control, their brain part. So you can, as we say, you can imagine even building neural networks from building blocks, from physical building blocks. Like in this case, we would have build a what we call a spiking neural network with this building block. So we would imagine here, we would have from the top here, we would have some input neurons from a sensor that would be input to this. They would send their from the spiking neuron. When this neuron would spike, it would have this excitatory neurons, the black neurons we see here. they would send their information to other neurons here. This would be inhibitory neurons that the C1 and C2 would get information from N2 and N3, and they would control the motors, the motor drivers. So they would be the C1 and C2, they would be combining the information that they got from above. So we would have a neural network, a spiking neural network, getting information from the sensors, sending that to a hidden layer, sending that to you would say an output layer that would be connected to the motor drivers. And that we can build in terms of the building blocks. Input to some sensor modules, we would have some intermediate hidden neurons like that, some combination neurons, combine 1 and combine 2, and then output to the motor drivers like this. So by this, physically creating a spiking neural network with the input, hidden, and output neurons. And this we can see, for instance, on this video on the right side, how we have this. There's a base robot there with the motors already built, as you can see, and then now he here is putting on the different neurons that we talked about. First, the lower ones, you can almost see they have the sensors on. These are, in this case, light sensors. Then he puts on some hidden neurons, the red ones, and then the yellow ones that he's putting on now are the output neurons that will then be connected to the motors. You can see the wire now being connected to the motors. And then having also the other one connect, you can see they're crossed as they are also crossed on the sketch here on this one here. And then he starts lighting up with a torch to do what we call Hebbian learning on the robot. So this is a self-learning neural network that does what we call Hebbian learning. So it if there's excitation on the output and on the input to a neuron in the middle, then it will reinforce the connectors there, going from to and from that neuron. So this spiking neural network will start doing that kind of very simple Hebbian learning, and you can see little by little, it by itself learns to approach this light source. So after a short while, he can start showing light sources further and further away from the robot, and the robot will start steering faster and faster towards the light source. And the only thing he has done here, he has built the physical body, and he has started to interact with the robot, with this spiking neural network, and it has by itself learned this behavior. So actually in one of the forthcoming videos, we'll look a little more into how we can create this kind of neural network, and this kind of different kinds of neural network training that will allow you to do this kind of systems that can adapt and learn how to do specific things. Now here you can see how this robot can approach the light source from far distance, even if a minute ago in the video it couldn't do anything at all, or it wasn't even a robot at that point in time. So important here, we can also discuss this a little bit further. What is happening here with this intelligent Lego blocks? If you think of this the blocks as intelligent Lego blocks that you can put together and you can physically manipulate to create solutions. This actually have important, as we touched upon, important pedagogical objectives, that we are expanding the sensorial experience of the children, that we're not only thinking about these very abstract things in the school class for the children, but we're making things physical for them, as you saw with the, for instance, the Fable robots, you saw with the modules down in Africa for the children, you saw with the intelligent Lego blocks and so forth. So in all these cases, we allow the children to manipulate with this their physical entities to enhance their sensorial knowledge of the reality, and they can do an active modification of the environment with these things. So this embodiment allows them to understand more about the environment. They can explore that, they understand the material and technical aspects, and even also some emotional and conceptual ones where they are creating structures that can express different things. Like you can make one that wiggles a lot, that they can interpret to be happy, one that goes slowly, they can interpret this is a little sad, or so forth. So we can imagine building blocks allowing many different things. And what happens here is that they're constructing, as we're talking about, making this isomorphic representations, which facilitate that they can think about these more abstract things in easier terms. This is a little similar to what we have on the right side here. On the top, the game 15 is where you have to make the sum of 15 in a line, or in a row, or in a diagonal, and that's, if you imagine putting up one number after another, that's a little bit challenging. You have the numbers from 1 to 9, and you have to put one number at a time. That's a quite challenging, cognitive, difficult game. But if you think of it, it's the exact same game as doing this one here, where you put the circle and crosses instead. And that's a very simple game. The tic-tac-toe game is very simple. Anybody can play that game, because we have changed the representation to be much more simple, and that lowers the cognitive load for people. So think about this when thinking about the interaction with physical modules may actually help you in this ways to facilitate these things for the users, for your users. So a good example of that is we can actually take this and bring this into different school training in places like deep rural areas in developing countries. In Africa, we make this African blocks, where in the schools they're using this for mathematical training, for language training. That you can imagine the blocks are representing different words. So when putting blocks together, they're creating sentences. When, for instance, they go from the elementary schools to the next level, they have to suddenly switch from talking Swahili to talking English, and that's a big challenge for many of the students. So what we do there is for the language training, we make this blocks, each represent a word, and they have to construct sentences with nouns and verbs and adjectives and so forth. And the system is controlling if their sentence structure is grammatically correct, and they get an immediate feedback on that. Just for one example, then they're creating in the universities different ways of using these African building blocks to create different ways of deploying this in their society for that. So again, this is an interactive problem-solving process, but where we, together with the universities, can go into the iterative prototype development to easily make new solutions for different challenges that they may find that they have. So other building blocks that are created in this process are these cubic ones that they said in order to help in different places, like in the children's hospitals. That may be a better structure to have than the other blocks that we saw before. And just as a final example that we'll touch upon later on as well, to understand this thing about building blocks that can have different shapes and different functionalities. So you see how the African building blocks and the structure of those inspired us to these cubic ones, inspired to make the next ones, that we then say, well, maybe we can use this for something totally different, namely for music construction, for constructing and deconstructing music. So in this case, together with Jakob Nielsen, we made this nice music eye blocks, where each block, as you can see down on the left, has a color that represent an instrument. So green is guitar, red is drums, light blue is vocal, blue is the bass, and so forth. And then when putting these together, depending on how they turn, you are creating the different turn, gives different expression of that instrument. So when guitar is like this, it's one sound of guitar. This is another sound of guitar. This is another sound of guitar. And then you can attach these together. When you attach them together, the sound emerges. So when you're building, you're physically building the body, you're building up the musical piece, but you can also deconstruct by taking them apart, so that you can listen, for instance, only to the bass and recognize, this is the bass in the song, then add on again. So you can add on, construct, you can take apart, you can deconstruct. And by that, you're learning about this more complex thing, which in this case is music and the musical pieces. That is maybe more easy to understand if you can even deconstruct this and take them piece by piece and understand this. So again, here we are building bodies and brains together, where the body is the physical shape and the brain is the processing of the music, and together the musical piece, the sound, the melody, the song is emerging from the right interplay between all these modules. So we can take that into a user interaction, like in this case, for setting up the rock museum in Roskilde. We made this building blocks, and it was a huge success for that. But we'll return to that in a future video, so we can go more into details here. I just wanted to show you this as another example of modularity and the building blocks, because the modularity is important here. And in summary, we can say that we have seen now how the modularity facilitates the Playware ABC. That you remember, our end goal and our wish is that we can create technology for anybody, anywhere, anytime. And what we have seen here today is, with the modularity, we facilitate that we can build bodies and brains, and we also, by that, facilitates that the user, as we could see in this example, is able with the modules to construct, combine, and create. And that makes it easy for the user to be part of this, as we talked about. To develop the intelligent response is the interplay between the user and the entity, in this case, the Playware or robotic system or what it may be. So it's those two together, the user and the thing we have created, that generates together in their interplay the intelligence and the intelligent response. So I want you would ask you to think about this as maybe for you a new way of thinking about intelligence, that intelligence is not only creating some intelligent software. That's not enough. It is the interplay between the software and the hardware and the environment, between the body and the brain and the environment. And we can even facilitate that in the creation of Playware, as we have seen with these examples here. So please think about those things, and hopefully it will help you to put things in quite nice perspectives. So thanks for listening and seeing in here.